Okay, now in this second module, we'll be covering Verilog syntax. We'll start with, but we'll be covering Verilog for synthesis, and then we'll be covering Verilog for simulation. So first of all, we'll be covering Verilog for synthesis. That means that the code that we write will be transformed into the components that we covered in the first block of this training. So we'll start with modules. In Verilog, module is a reasonable size replicatable block. For example, whatever component that you think that you'll need to use again, it's a good idea to make it a module. For example, you can think of it as a just like if you design your logic on breadboard and you use the ICs. So those ICs are replicatable components. You can have ICs of the same kind, many ICs of the same kind, and you can use that. Similarly, we can have a module and we can reuse it again and again. For example, in the last examples, the counter or decrementer or FIFO that we design can be used as modules because they can be used in multiple situations. Uh, okay, so for example, we want to write code for FIFO. So what we'll do is we make a text file and change its extension to .v, and we'll give it a name, for example, FIFO.v, and we just write down the inputs and outputs. So in FIFO we had data in, push, pop, data out, FIFO full and FIFO empty signals. So in that file we start by writing module space name of the module, in this case it's FIFO, and then we have parenthesis start and parenthesis end followed by a semicolon, and then we have end module. In these parentheses we write here we write the inputs and outputs, and here we write code for modeling Verilog, modeling the FIFO. So what we do is we just write inputs and outputs. That's the port list. Uh, so if something is input, we write input. If something is output, we write output. And this is a comma separated list. That means that in the last thing we won't have a comma. And if something is 1 bit wide, we don't write anything. And if it comprises of multiple bits, for example, if we have 16-bit data, we'll write it 15 colon 0. We read it 15 down to 0. So that means 0, 1, 2 up to 15 will be 16 bits. So in this case, we are assuming that our FIFO was 16-bit, can store 16-bit data samples. Okay, so this can be a module, and then we'll write code for modeling FIFO here. Before we write code for FIFO, I want to go into how modules are used. For example, if we want to have to implement this logic design diagram, so this diagram also has this counter here. So this counter can be a separate module as well. If we think that we need to have a up down counter, we'll be using an up down counter later on. So we can write another module counter with inputs increment, decrement, and count is the output. So how would we use that counter in our FIFO? That's what I want to explain here. So let's say I am writing this code for FIFO and assume that I have already written code for counter. So what I have said is that the counter is kind of, every module is kind of a chip, and we want, just like we place that chip on a breadboard, we can instantiate that module in our code for FIFO. So that's how we instantiate it. So writing this code means that we have made an instance of that counter. So what we do is we first of all write the name of the module that we want to instantiate. So name is counter. Then we give instance a name. For example, counter instance 1, or I can give it any name that I want. Then we tie the ports that are here, increment, decrement, and count, with the ports in FIFO. For example, if you remember the design, increment needed to be connected to push signal, decrement needed to be connected to pop signal, and count needed to be connected to count. So it doesn't matter if it's the same name or a different name, because we are now inside this module, and that is FIFO.v, so we can connect it to them. And these things will be generally declared as wire or reg. We'll discuss later on how we declare these things. So if we had two counters, we didn't have two counters in this case, but if we had two counters, then we can have another instance with something like this. Okay, so if we have two counters, then we can instantiate two counts, and then we can have different signals. If we want to increment, decrement, we can have some common signals. Then we can have some common. It will depend on the design that we are making. In this design, we only needed one counter. But what I wanted to show was that we can have multiple instances, multiple counts, just like we had multiple chips on a breadboard of same type. So so that's it. So we only need one counter. So that's how we instantiate a model. So in summary, module is a block that can be reused and replicated. So now we come to writing Verilog code for what's inside the block, inside the module. So we'll cover basic building blocks and how we write code for each of the building blocks. So these were the basic building blocks that we covered: gates, muxes, demuxes, registers, memories, arithmetic operations, and state machines. So what we're trying to do here is that we are using words and characters written in a file, and that characters will infer uh, some hardware when we synthesize it, and it will model that hardware when we simulate it, when we'll try to run the code in simulation on our computer. So if we want to model a gate, we normally use always at static, and then we use begin end. And if we want to make an AND gate, we use A is equal to B and C and D. So just those who already know C know that in C this ampersand sign is used for AND. So in Verilog it's also used for AND. And it works in exactly the same way. It's bitwise AND by default, and if we use double AND, it will be logical AND. But normally we don't use logical AND when we are designing logic. Similarly, for OR, we'll be using this bar symbol that we use in C. For XOR, we use this cap signal, that symbol that will XOR multiple things. For NOT, we use tilde sign. So these are all bitwise operators in this case. Uh, this begin end, you can think of it as brackets in C, starting curly bracket and ending curly bracket. And this always at static is something that we always use. That's called a procedural assignment, but it doesn't matter what we call it. You should almost always use this. Next thing is multiplexer. So that means whenever there is a gate, we can use this syntax and it will infer a gate. So if we want to make a multiplexer, then we again use always the static begin end. So that's brackets. And then just like in C, we have a switch case statement. In Verilog, we have only a case statement. We put a case, and parentheses, we put the name of select line signal. So in this case, it's address. And then to end the case, we have to put an end case. And then we write this kind of syntax. Ignore this 2-tick-D at the moment. What we're doing is that we are 0, 1, 2, and 3. We are saying that out will be connected to A if select line is 0. Out will be connected to B. Assume that this is A, B, C, and D. So this is the syntax that if the select line is 0, we connect it out with A. If it's 1, we connect to B and C and D, so on. So now what is this 2-tick-D0 thing? So this is the way Verilog stores the data values. So if we write 8-tick-D 4 zeros underscore 1010, so this 8 means it's the width of the bus. This tick is ignored. This B means we are writing the value in binary format. There are 4 options. We can write it in binary, octal, decimal, or hexadecimal. Then these are the values, and among the values we can use underscore as well. That will be ignored, but it is very useful, especially when we are looking into bit fields and we want to see, let's say in a 32-bit number, bit 13 and 15 separately and 19 and 20 separately, then we can put underscores to differentiate different bits. So unlike C, we can add underscores inside numbers. So even if I write this int B1010, that means that it will be an 8-bit bus with this value at the input, that is 2 ones, and rest of the values will be 0. If I write this way, or if I write it D10, it will mean the same thing. It will be internally translated into binary, and binary of 10 is 1010 that we saw in the previous value. Also, if I write it HA, it will also mean the same thing. At times we use X's in these values. X's means don't care. For example, in a mux, if we want to place some values as don't care, that we don't care whether this bit is 0 or 1, then we can use X. So, but we can only use it in hex or binary. Okay, so now similarly, we can write code for demux. For demux, we also use always at static begin, and just like the cases before that, and then we have similar structure with case and to be 0 and so on with end case. But here we have a little bit of different syntax, and it's not necessary that we use this syntax. I'll tell you another way as well, but I also wanted to cover concatenation, how this statement is written. So this is called concatenation. For example, so this is a separate example to explain what concatenation is, that will make you understand the last slide again. Let's say we have 4-bit signal A, 3-bit signal B, 1-bit signal C, and I want to connect it to, let's say, 14-bit data bus. But I want to connect it this way, that I want to have 4 bits of A in the MSBs, then 3 bits of Bs next, and 4 zeros, and then C is replicated 3 times. So what we do in Verilog is that if we want to concatenate things this way, we put a curly bracket and we write data in is equal to, and then within the curly brackets, whatever we write left to right will be concatenated left to right. For example, if I want A and B, then I'll write A comma B, followed by I want to have 4 zeros. So for 4 zeros, I'll have to write 4 tick D0 that, or B0, or whatever 0 hex 0, but it means that there are 4 bits which are 0, and then I have to replicate C 3 times. If I want to replicate it, I'll have to put C in curly brackets, write 3 outside it, and then put another set of curly braces. So that means that I'll be replicating C 3 times, and this statement will mean that the connections will be correctly made. So now if we look at this logic that I have written here, so what I'm saying is that this input is in, and A, B, C, and D are the outputs. So if A, B, C, and D are the outputs, what I'm saying is that assign A, B, C, D in such a way that we have in first, and then we have 3 zeros. That means that in will be connected to A, and then 3 zeros will be connected to B, C, and D. It is important to connect zeros to the rest of the outputs as well, because that's what will happen if we want to make a demux. If we don't connect it, that will infer a latch that we never want. That will mean that these outputs won't be asserted. If I only write in A is equal to in here, that means that we haven't asserted B, C, and D. That will indicate to compiler that we want to hold the previous value, and in that case it will make a combinational feedback that we never want. Similarly, in the next line we have written that we want to connect in such a way that first value will be 0, so A will be connected to 0, then B will be connected to in, and that will be followed by 2 zeros, and so on for the rest of the values. Okay, so that's how it works. It's perfectly okay if instead of writing this syntax, if we write begin and end. So begin and end means if we have more than one statement, then we put just like we put curly brackets in C. So we put begin and in into typically 0, and here we write A is equal to in, B is equal to 0, C is equal to 0, D is equal to 0, and in to D1 we again put begin and now we put B is equal to in and put rest of the values to 0, and so on. it will still work fine. It will infer a demux as usual. Okay, so next component that we studied was register, and if we want to model a register, again we use always at, but not static this time. We use always at pause edge clock if we want our register to work on rising edge of a clock, and if we want to work it on falling edge of a clock, then we use neg edge clock. Normally, most of the times we use pause edge clock, unless we are interfacing with something outside the FPGA, then we normally use neg edge of clock as well. Another change in syntax is that instead of equal to, we have this, we call this non-blocking assignment. This is kind of an arrow symbol, that less than equal to symbol, kind of an arrow symbol. This is called non-blocking assignment. So if I want to make a register with these names, then I'm saying that if there is a reset signal, then reg out should be 0. So that output should be 0. Otherwise, register should have the value of whatever the value is here. So on every rising edge of clock, this reg out will either be 0 if reset is asserted, or it will input the value of whatever value is at the input. If we have an enable signal as well, just like so first of all, we have to remember that registers is inferred only if we use always at pause edge or neg edge clock, and when we do that, we should always use non-blocking assignment instead of a blocking assignment. In the previous examples, we always use blocking assignment. So if you don't use that, there can be differences in your simulation and actual synthesis, because this will not model registers properly if there is a non-blocking assignment. If there is an enable signal as well, then we can use else if and use that enable in the bracket. So that will mean that if there is a reset, then register will be 0. Otherwise, if there is an enable signal, it will sample the input. Otherwise, it won't. So that's how we write registers. So remember this point. Register is always made by using always at pause edge clock. For rest of the values, we use always at static. Always at static means you can think of it as that it's always running. Whenever there is a change in input, output will be changed. But with always at pause edge clock, we only work on edges of the clock. Similarly, if we want to make an adder, again we'll use, it's a combinational circuit. Whenever there is a combinational circuit, we use always that static. So I can write C is equal to A plus B, that will make an adder. Similarly, C is equal to A minus B will make a subtractor. C is equal to A multiplied by B will infer a multiplier. At times we want to use, most of the time that this works fine, but at times we want to specifically use some adder or multiplier from a library. So in that case, that module will be available to us, and we'll use that instance of that module instead of writing A is equal to C is equal to A plus B or so on. Okay, so the names that I've been using in these slides, the ABC, these are not really good names. What we want is that names should be a bit descriptive, and naming convention is that you can use alphabets and numbers, but most of the times we use small alphabets, because at times we are working with some old compilers which are not case sensitive, and that can lead to some problems at times. Basically, Verilog is case sensitive, but with hardware tools, we at times have to go to the compilers that are not case sensitive. Okay, so just keep in mind that whenever you want to make an adder or subtractor, you should know that to be safe, that if you want two numbers, output should be one bit greater than that. For multiplying two numbers, the output size will be doubled, uh, and we can avoid that if we already know that input output will always remain in the range. Then we can make it whatever we want. Okay, so one thing that I haven't covered is how will we declare these variables. So these variables can be declared as reg or var. So this reg is kind of an idiosyncrasy in Verilog. If I had been making Verilog, I would have used only one type, maybe wire. There was no need for reg. So don't confuse reg with register. It has nothing to do with register. Uh, Whenever we assign something in an always block, for example, always at static or always at posage clock, the thing that is assigned, I'm not talking about on the right side, but the things on the left side, this has to be declared as a reg. So in this case, this is a purely combinational circuit. There is no register, but I have to declare C reg because this procedural assignment, that is always the static kind of assignment. That means that I have to declare it as reg. There is another way to make the same circuit that I haven't covered, that is use of assign statement. So assign is also, if I write assign C is equal to A plus B, it will also make the circuit. But in assign, we can only have one statement. In always at static, we can write begin and we can have multiple statements. So in assign, we only have one statement. And in that case, if I use assign to assign value, some value to C, then this C needs to be declared as wire. Practically, this code and this code means exactly the same thing. This reg, and remember, this reg doesn't mean register. If I really want to make a register at the output of adder, then I have to put this always at posage clock and a non-blocking statement here. That will mean that this is a registered output of adder. If I use always a static, there is no difference. What about A and B? I told you that on the left side, whatever is assigned, it has to be declared as reg if it's an always block, or a wire if it is an assigned block. So what about A and B? So A and B will be reg if A and B will be coming from some other piece of code, and in that piece of if that piece of code is an always block, then A needs to be a reg. If that piece of code is a assigned statement, then A needs to be a wire. Okay, so now we'll cover what are, we have covered all the basic building blocks, how we write code for them. And so what we do normally in hardware design is we make a design diagram and we code all the building blocks. It doesn't matter in what sequence we code them. We just name all the wires in the design. We declare the module and port list, and we start coding logic elements one by one. We just need to code everything. We don't need to take care of any sequence. We just need to cover everything. And normally what I do is, while I'm coding, I keep declaring variables on the fly. So writing Verilog code is a very simple thing if you know the syntax. So in if we write that a few times, then it just becomes a simple process. The main thing is coming up with a design. After that, we can just, it's a dumb process to write a code. So let's do an example in which we'll write the code. So here is the incrementer decrementer counter that we made for FIFO. So if I want to make a module of this, what should I do? So I first of all needs to label all the wires that are in the design. Then I need to create a file counter.v, and in that file I can write inputs and outputs. Most of the times clock and reset are implicit. We normally don't show it in the design that this is a clock or a reset. We know that if there is a register, it will have a clock, and mostly registers have reset. If we know that we don't need a reset, we can initialize it to zero value, but avoid the reset. It helps at times, but most of the time there will be a reset and clock. So we can see that we have increment, decrement, count, and clock and reset as input. Count is output. So ignore the reg for the moment here. Just assume that it's output 3 down to 0 count. Now I can start coding one by one. I can start from wherever I want. So I will start with this register. So say this gate, this is a OR gate. Pause for a moment and think about it. How do we write code for an OR gate? For an OR gate, we use always that static and we use the OR symbol. So that's the code. So this name is enable. We are ORing increment and decrement. So we use always at static, increment or decrement. Since this is just one line, so just like in C, we don't need begin end if there is only one statement. And then we can think whether we need to decrement we need to declare something or not. Increment and decrement are already declared. I need to declare enable. What should be enable declared as? Wire or reg? It should be declared as reg because it's an always block. It's not a register, but it's an always block. That's why we are assigning it an always block. So I need to declare it as a reg. Next, I want to code that mux. How do we write code for mux? We write always at static and case end case. So we write always at static, case end case. And if the slackline is increment, if increment is 0, we want to decrement it. If it's 1, we want to increment it. We could have used terms increment out and decrement out, and then we could have written code for decrement out is equal to count plus 1 and increment out is equal to count count minus 1 and increment out is equal to count plus 1. But what I have written is that I have written this incrementer and decrementer in the same block. So mux out is equal to, this is mux out is equal to, if it's 0, increment is 0, then count minus 1. If increment is 1, that is we want to increment it, then it's count plus 1. So actually we have coded mux as well as these two incrementer and decrementers. Again, we need to declare this mux out, and since it's a always block in which we are assigning it, so we have to declare it as a reg. Next, we are only left with this register, and this register, how do we write code for a register? For register, we use always at pause h clock. And do this register need an enable? Yes, it does. So if there is an if reset, we want to set it to 0. Otherwise, if there is enable, we want to store mux out in that register. So that's this hash one you can ignore for the moment. That is something that we used to write for modeling setup and hold times in register, but you can ignore it for the moment. So when we write that, now we need to think about it, whether we have declared it or not. So count is output. So we have already declared it as output. Since this is an always statement, we also need to put this reg here because we are assigning in an always block. Okay, so if it has been in an assigned statement, then we didn't need to put this reg here. Okay. One thing that I would want to cover, I'll go back a bit where we did the counter example and push pop thing. Go back. Okay, so here we were using this instance here. So when we are instantiating something, that we instantiate a module in another module, then all the outputs should be tied to a wire. That's also something that you should note, that that push and pop needs to be the push and pops are inputs, so they can be anything, depends whether in the code I have written push as in an always block or assigned block. That will determine whether it's a reg or a wire. But for the outputs, so count is output of this module, that output will always need to be a wire because we cannot assign it in this module because it's output of this counter. So we have to use wire here. So that's something that I should have told. Okay, so last thing in this block is about arrays. So I'll just quickly go back to the example and arrays. We can also use arrays in our design. For example, if I want to write code for the FIFO that we designed, so I can write it this way. If it's a 32-bit input, then I'll write 31 down to 0, FIFO edges. And then after that, I'll write about depth of the FIFO. Normally, we write 0 to 3 if it's 4-bit, 4 deep. If it was more deep, then we can change this 3, and that's how we write the edges. Just like in C, we write int something and then we write a number. So instead of a number, we write 0 to something. And instead of int, we specify explicitly what is the width of that variable. We can use it in two ways. For example, if we want to read the value from that, so if I write a is equal to FIFO edges and 0, that means that I want to read the first register of 32-bit byte. If I write something like this, that 0 15 down to 0, that means I want to read for 16 LSBs of 0 register. So that's how we write. Similarly, if we want to write on for 16 LSBs of register 0, I can write this. So the first number will be telling which register number I'm talking about, and the next will be telling about this the bits that I'm interested in. I'll also want to cover alternate syntax for mux. If I have used an array, then for example, if I write data out is equal to FIFO edges and then in square brackets I write address, this effectively means that I'm making a mux with address as a select line that is selecting between all the edges and connecting it to outputs. So at times writing using arrays makes code more compact, that I generally like. Okay, so I'll stop here and we'll cover verification in the next